This video is about projectile motion. So here's a projectile, and here's some motion, and here's some data. Now we'll gather some more data. First of all, a vertical drop, and second, a bounce in the opposite direction. Now we'll analyse the data. There are 5 major points to be learned from these data sets. The up and down freeze frame shots are equally spaced. Moving the balls to the right at constant velocity produces a parabolic trajectory. The trajectory is symmetrical about the zenith. The horizontal vectors are equal, the vertical ones are not. The horizontal and vertical velocities are completely independent of one another. These points allow clear analysis of projectile motion problems. So let's do one. We have a projectile travelling at 20 metres a second, 37 degrees above the horizontal. And we'd like to know the height, the time, and the range. The diagram is in polar form, so the first step is to convert that to rectangular. So for ux, we'll have v cos 37 or theta, and for uy, we'll have v sine theta. So v cos theta is going to be 20 metres a second times cos theta, cos 37, which is going to be 0.8, which gives us 16 metres a second. For uy, we have v sine theta, which is 20 times sine 37, which is 0.6, which is equal to 12 metres a second. We can find the height by making use of the equation v squared is equal to u squared plus 2as, but since we're using gravity, that will become v squared is equal to u squared minus 2gs. So we make use of the fact that during the trajectory, the projectile will be stationary momentarily at the top, so the vertical velocity will be 0 before it comes down again. So v squared will be 0, which will be equal to the vertical velocity, which is 12 metres a second, which is going to give us 12 squared, which is 144, and that'll be minus 2gs, which is 19.6 s. From that, we deduce that S will be equal to 7.35 metres. For the time, we just need to find the uptime. So there's an uptime and a downtime. They're both equal because of the symmetry of the situation. So if we find just T up and multiply by 2, we'll have the total flight time. Okay, so let's do that. So we begin by using V is equal to U plus AT. Since the projectile will be stationary at the zenith, the implication there is that 0 will be equal to 12 vertical velocity minus 9.8 t, which implies further t up is going to be equal to 1.224 seconds, and t total will be twice that, so t total is going to be equal to 2 times 1.224 is equal to 2.45 seconds. For the range, we multiply the horizontal velocity, which doesn't change during the whole of the range, times the total time. So we have Sx for the range is going to be equal to Ux times t total. So Ux is 16 metres a second times t total, which is 2.45. And that gives us 39.2 metres. You need to ask yourself, why would we do one of these? The profoundly overwhelming majority of projectiles on Earth are from weapons like this field gun. It takes no imagination to see that the range here is critical. The range is a function of elevation of the barrel and the velocity of the projectile. Where angles of inclination and declination around 45 degrees are equal, their ranges are equal. In this example, 60 degrees and 30 degrees are both 15 degrees away from 45. If we divide the trajectories into two categories, those 45 degrees and over and those below 45 degrees, we see there is only one way to reach the maximum range and precisely two ways to reach the lesser ranges. This time we'll introduce launch height into the problem and examine the use of the equation S is equal to ut plus a half at squared. So we have a problem where there's a cliff 140 metres high. We have an angle of elevation of the weapon at 37 degrees and the muzzle velocity of 100 metres a second. And we'd like to find the time and the range. So when we're using S is equal to ut plus a half at squared and the A is actually gravity, the coefficient of t squared has to be negative. Now this has the effect of making the parabola a frowny face rather than a smiley one. The displacement above 140 metres is 0. It's gone up and it's come back down. So the first step is to get all of these signs right and place them into the equation. So S is going down, negative 140. U, the vertical component of the velocity, is 60 metres a second, going up. So it's 60t. Now the half A becomes a half G, which is negative and 4.9, so this is negative 4.9 t squared. Now if we equate that to 0, we get negative 4.9 t squared plus 60t plus 140 is equal to 0. So we can read off the quadratic coefficients. A is 4.9, B is 60, that's negative 4.9, B is 60, positive 60, and C is 140. Using our graphics calculator, we can solve the quadratic, and we get 2 times, so T becomes 14.3 seconds, or negative 2, which we'll delete. So we use that time to find the range, and the range Sx becomes velocity, horizontal velocity times time, which is equal to horizontal velocity is 80 metres a second, so it's 80 times 14.3, which is 1144 metres. Tick. This time the barrel is parallel to the ground, so theta is 0. So cos theta is going to be 1 and sine theta is going to be 0. So the horizontal velocity is 100 and the vertical component of the velocity is 0. We proceed as before. S is still negative 140 because it's going down, we're measuring down. Vy is 0. So we've got 0t. Then we still have negative 4.9 t squared. This time we don't need to solve a quadratic. So the implication there is that 4.9 t squared is 140. So t is going to be equal to the square root of 140 on 4.9, which is, when we do it, is 5.35 seconds. Notice it doesn't matter which way the projectile gets to the ground. The time is still going to be the same because the vertical and horizontal components are completely separated from one another. So it can go that way as far as it likes, and it's still going to be 5.35 seconds. Or it can go straight down, and it's still going to be 5.35 seconds. So finally, we get the range Sx is going to be equal to Ux times t. Ux is 100 metres a second, so that's going to be 100 times 5.35 seconds, which is going to be 535 metres. Tick. Lastly, we have the projectile being fired downwards at an angle of negative 37 degrees. So we proceed as before, but this time we've got Ux is equal to cos 37 times 100, which is 80 metres a second. Uy is sine negative 37, which is 100 times negative 0.6, which is negative 60 metres a second. So we proceed. Negative 140 for S, because it's going down, is equal to the negative vertical velocity, which is negative 60 metres a second. And as always, when we're using gravity, half at squared becomes a half gt squared, which is negative 4.9 t squared. So if we equate that to 0, we get negative 4.9 t squared, negative 60 t, positive 140, as we transpose it, is equal to 0. once again we have our quadratic coefficients. So A is negative 4.9, B is negative 60, and C is positive 140. So plugging those into our graphics calculator and solving gives us 2 times again, t is either 2 seconds or negative 14.24 seconds, which we reject. So the range Sx is going to be equal to Ux times t, which is going to be 80 times 2, is going to be 160 metres. Done. For each of the trajectories, plus 37, 0, negative 37, there is an associated parabola whose roots and y-intercept are shown rounded out in the table. Notice that only the positive section of the parabola is used for modelling projectile motion close to the Earth's surface. And also notice that in each case the y-intercept is 140 metres, corresponding to the height of the cliff. The symmetry of this result is due to the launch angle being plus or minus 37 degrees on either side of the horizontal. Finally, the effect of air resistance is very pronounced on fast-moving projectiles. You can check this for yourself by using the information on the boilerplate of this howitzer 105mm field gun. At 45 degrees, the theoretical range is far greater than the stated 10 kilometres. So how much greater is it? Give it a try and see what you get.